B3. How many more problems are there? Oh man, you guys have so many questions. I'm trying to get through all the ones that got first votes. Um, and so that's still B3, A6, A7, and C9. All right, so B3. I'm not gonna go through B3 just because it's the exact same approach that you would do for everything else. Right. So actually, you know what? I'll just go through one thing, right? So in this case, I'm only simply asking for calculating the energy of the first 11 levels. So as I mentioned before, right, what you can do is if all the L's are exactly the same, right? If all those are the same, you can just pull that out. And so you can just simply make, right, the equation being h squared over 8ml squared times n squared of x plus n squared of y plus n squared of z. In those cases, right? And so, whatever, I'll just do it, right? So if we have the E11 level, right, in these cases, in this case, right, we can just go ahead and we can calculate that out as a constant in this case, right? So we have H, right? So that's 6.626 times 10 to the negative 34 joule seconds squared over 8 times, right? We're doing an electron in this case. Oh, I guess I didn't specifically say electron, so I wonder if that's where people are getting confused. But I meant to include electron. I think in my brain that was implied. So 9.11 times negative 31 kilograms times the length, right? So the length is the same for all of them. So it's 2.8 angstroms. And so that's 2.8 times 10 to the negative 10 meters. 2.8 times 10 to the negative 10 meters. And so that comes out to being equal to, all right, 2.8 times 10 to the negative 10. That comes out to being equal to 7.684 times 10 to the negative 19 joules. And so we can just simply use that value, right? We can plug that into here. So we can have 7.684 times 10 to the negative 19 joules times, right? And now we just have this part, right? So it's 1 squared plus 1 squared plus 1 squared. Okay, so that's, 3. So we have x times 1 squared plus 1 squared plus 1 squared. So what we get is an energy of 2.31 times 10 to the negative 18 joules, which should be what I have on the key. Yes. Right, so you have that right there. And then, you just do the same thing that we had done with the 2D particle in a box, where, you have your one combination where you have 2, 1, 1 in this case, right? So you just use that same value. So 7.684 times 10 to the negative 19 joules, right? So that becomes 2 squared plus 1 squared plus 1 squared. So that comes out to being equal to 4.61 times 10 to the negative 18 joules. Right, and that's what I have on the key. Yep. Right, and so then that's going to be the exact same for the other values, right, that are very similar, right, where you have then the 1, 2, 1, and then also the 1, 1, 2, right, because all of those are going to be degenerate, right? There's the only difference between them is just simply which one has the higher n value, but because mathematically they're all going to end up with the exact same energies, they're all going to be degenerate. And so they'll all have the same values in those cases. On a test, would we be given this equation for energy, or should we know it intuitively? I think you guys would be given it in these cases. So I think there was like a 2D or 3D particle in a box problem last semester. Thinking back now, I do recall, I think, seeing one on there, and I think the energy equation was given in those cases. So Excuse me. So I think you would be given them, but I mean, all it is just simply, right, you're just simply stacking up the different dimensions to it, right? Because the normal particle in a box on its own, really, if you think about it, is just simply this part right here. And then if you're like, oh, I'm going to add the 2D part, well, I'm just going to add plus n squared, L squared over L, thing for that direction, right? And then 3D is like, oh, well, we'll just add the Z direction to it too, right? And the same thing up here, right? This right here is just simply the 1D particle in a box. And then for the 2D, right, we're just simply going to multiply the wave function for the Y direction to it. And for 3D, right, we're just simply multiplying in the third, dimension as well. But I think you would just be given those on the exam. But it's still helpful to think about like what the components are. So when it comes time to like being like, how do I explain my answer, or how do I approach maybe thinking about it, right? You're just, because you're just applying the same things, the 2D and the 3D are not that much more complicated than the 1D, right? They're just basically, you're just adding one more dimension, but you can break it down into two 1D parts, and then you're just like smushing it into a 2D or a 3D part. Yeah. But that's all you do for B3, right? And then you just work your way through the different combinations, right? And again, the one thing that I had mentioned for the 2D particle in a box, it's very easy to fall into the trap where if you're going like, 1 1 1 1, 2 1 1 2 2 1 2 2 2, to then be like, oh, well, next should be like 3 2 2 or something like that. That's not right? So the 2 2 2 is actually higher in energy compared to the 3 1 1. Right? Because the 3 1 1, the n, combination of all the n things is actually, right, 9 plus 1 plus 1, which is 11. Whereas in the case of the 2 2 2, what it is, right, is 4 plus 4 plus 4, which is 12, right? So there's actually, the 3 1 1, and, other related ones are actually lower in energy compared to the 2 2 2 in the 3D particle box, right? So that's always an important thing to think about, is that, it's very easy to get into that, rote approach where you're just like, oh, I'm just going, down a certain row, without thinking about, well, how do the other rows actually, contribute and approach these things. So, cool. All right, so that's B3.